Section 5.5, the substitution rule. If u equals g of x is a differentiable function whose range is an interval I and f is continuous in I, then the integral of f of g times the derivative of g is equal to the integral of f of u. So this should look pretty familiar. It's kind of like if you've got f of g of x and you want to take the derivative. So then you take the derivative of this thing, assuming that it's a function of g of x, and then you multiply by the derivative of what's inside. And then that'll equal the derivative of f of g of x with respect to x. So this is basically the chain rule, but in reverse. We start with this thing over here, and then we end up with the original function of the composition. You might be saying, hey, wait, it's missing that derivative, but this is an integral. So we're saying you go backwards. So this thing was the derivative of some other function to begin with. The cool thing about this rule is that, let me erase this, it implies that if you've got f of g of x and u equals g of x, then we can do something with these terms over here. In general, we don't really assign any specific meaning to them. They're just part of notation. But this formula implies that you can actually write that du is equal to g prime of x dx. Because this part over here becomes du if this part over here becomes u. So basically we can treat these dx and du inside of the integral as if they were differentials. Let's do the proof of this real quick. If lowercase f is the derivative of capital F, then by the chain rule, we have the derivative of f of g of x is f of g of x times g prime of x. See, this big F becomes little f when you take the derivative. So if u equals g of x, then we have that the integral of this is f of g of x plus c, because this integral is just an antiderivative by definition. And little f is the derivative of big F. So that's just f of u plus c, which is the integral of f of u du. So basically now we have a way to do any kind of integral of a complicated composition of a function, assuming that we also multiply by the derivative of that composition inside of the integral. So let's do a couple examples. Let's try to find the integral of x cubed times the cosine of x to the fourth plus 2 dx. It's maybe not immediately obvious, but if we let u equal x to the fourth plus 2, we treat du and dx as differentials, differentiate both sides, and get du equals 4x cubed dx. So we have an x cubed and a dx in here, but we do not have a 4. So we divide both sides by 4, and we get that 1/4 du is equal to x cubed dx. So now we can replace x cubed dx with the substitution 1/4 du. So x cubed times the cosine of x to the fourth plus 2 dx is equal to cosine u times 1/4 du after the substitution. Now it becomes a little bit more obvious what we're looking for from the outset. We're looking for a function that has a nearby derivative. Well, this x to the fourth plus 2 has a derivative of 4x cubed. X cubed is right there. It's very close to 4x cubed. All we had to do was divide by 4. So that's typically what you're looking for when trying to figure out what to make u equal to for your substitution. Look for something that has a derivative. So let's keep going now. We'll take out our 1/4. So we have just 1/4 times the integral of cosine of u du. which is 1/4 times sine of u plus c. But our integral was in terms of x, not u. So we have to finish up by substituting back for what u is equal to, so that our answer is just in terms of x. So we replace u with x to the 4th plus 2, because that's what we said u is equal to, and we don't forget our plus c. Let's do another example. For this problem, you're probably wondering, what should I make u equal to? Well, if I do 2x plus 1, then when I take the derivative, I'll just have 2 dx. I have 1 dx, so I just have to divide by 2. So it seems like that should be a good choice. Let's let u equal 2x plus 1, take derivatives. We get du equals 2 dx, and then half du is equal to dx. Substituting in, we get that the integral of 2x plus 1 dx is equal to the integral of square root u times half du, which is equal to half of the integral of u to the 1/2. Writing it as a power allows us to use the reverse power rule to get half times u to the 3/2 divided by 3/2 when taking the antiderivative. We remember our plus c, and then this equals 1/3 u to the 3/2 plus c when we simplify. Again, we have to remember that we're in terms of x, not u, so we go back in, we replace u with 2x plus 1, so we get 1/3 times 2x plus 1 to the 3/2 plus c. And it should make sense that if you would take the derivative, this would hop out in front, and then you would apply the chain rule, multiply by 2, because that's the derivative of what's inside. This would reduce by 1, and it could leave you with a half, which is a square root, so you would return to that. However, this is not the only choice of u you could have made. What you could have said is let u equal the square root of 2x plus 1, in which case du becomes the derivative times dx, so that's dx over the square root of 2x plus 1, because the derivative is 1 over square root of 2x plus 1, and then we just put dx on top to save space. If we multiply both sides by square root 2x plus 1, we get that dx is equal to the square root of 2x plus 1 times du, but we said that square root of 2x plus 1 was equal to u. So we can replace square root of 2x plus 1 with u and get that this is equal to u du. And now we have a complete substitution for dx. Notice if we had left it like this, we wouldn't have really gotten anywhere, because we would have replaced dx with something in terms of x and something in terms of u, and we would have had 2 variables in our integral, which is no good. So we needed the whole thing to be in terms of u. So now we can rewrite it. 2x plus 1 times dx is equal to the integral of now u times u du, right? Because this is u du, so altogether the substitution gives us u times u, which is u squared. So that's very easy to integrate. Just u cubed over 3 plus c, and that's just 1/3 times 2x plus 1 to the 3/2 plus c, which is exactly what we got before. Notice that this substitution was probably way easier to come up with right off the bat, because you would think, oh, let me just substitute from inside of the square root. You wouldn't immediately think to substitute for this guy, especially since when you take the derivative, it looks like such a mess. But in this case, if you chose the more complicated one, it actually ended up being a simpler integral. So sometimes you have to mess around with what you're actually choosing u to be equal to, and sometimes you have to change your mind and try another definition for u so that you can try to do your integral. It takes a lot of practice. let's find this integral. Well, u equal 1 minus 4x squared. So if I do that, then I've got derivative of 4x squared is 8x. So that's an x I can just divide by 8. So we'll take du minus 8x dx. So now I can say that x dx, just switch the order, is equal to minus 1/8 du. And this is something I can substitute in for right over there. So let's do the integral now. Okay, using our substitution, that's minus 1/8 integral 1 over square root of u du, which is minus 1/8 times the integral of u to the minus 1/2 by replacing our square root with an exponent. So we do our reverse power rule for the antiderivative, and we get minus 1/8 times 2 rad u plus c, which is minus 1/4 times the square root of 1 minus 4x squared when we substitute back. How about if we have the integral of e to the 5x dx? Well, if I take the derivative of 5x, it's just 5. So I would get 5 dx. So then I'd replace the dx, I'd replace the 5x. So I think that looks like a good idea. Let's let u equal 5x. Then du is equal to 5 dx. So that means that dx, which is what I want to replace, is 1/5 du. So let's look at this integral now. It'll just be the integral of 1/5 e to the u du, which is such a small change, but it's so much better because I know exactly how to integrate that. The derivative of e to the x is just e to the x, so the integral of e to the x is just e to the x, so the integral of e to the u is just e to the u. Replacing u now, we get it's 1/5 e to the 5x plus c. And if you were to take this derivative, you would get e to the 5x times the derivative of 5x, which is 5, which would hop out and cancel with that. So you would be right back over here. For this example, it's a lot less obvious what to make u equal to. You have to really think about it, because if you make it equal to 1 plus x squared, then when you take the derivative, you get 2x dx, and there isn't any immediately obvious x dx here. There's an x to the 5th. So what you might want to do is rewrite this as the square root of 1 plus x squared times x to the 4th times x dx. Now you have something you can substitute in. So let's try doing that. Let u equal 1 plus x squared. Du will be equal to 2x dx, like we said. So that means that x dx is equal to half du. So we'll replace that with half du. We still have this x to the 4th to worry about, though. Well, we said that x squared is equal to u minus 1 by saying that u is equal to 1 plus x squared. So x squared is u minus 1. So now we have something we can substitute for x squared. But if we just squared that, we'll have something we can substitute for x to the 4th. So let's do this integral. We've got 1 plus x squared times x to the 5th dx equal to square root of 1 plus x squared times x to the 4th times x dx. We replace the square root of 1 plus x squared with the square root of u. We replace x to the 4th with u minus 1 squared. And replace x dx with half du. Doesn't look like we made progress, but we actually did make super progress because we have no more of this disgusting giant root. Our new square root is just on a single u. Way easier to work with, because now we can say that this is half of the integral of square root of u times u squared minus 2u plus 1 du, which is equal to half of u to the 5 over 2 minus 2u to the 3 over 2 plus u to the half du. And you might say, well, that's so gross, but actually that's just a whole bunch of power functions. Those are so easy to integrate one by one. So we do that. We get the antiderivatives of each one of those, which is half times 2/7 u to the 7 over 2, because you just increase it by 1, divide by 7 over 2. Then it's minus 2 times 2/5 u to the 5 over 2 plus 2/3 u to the 3 over 2 plus c. Now we have to not forget to substitute back. So we get 1/7 1 plus x squared to the 7 over 2 minus 2/5 1 plus x squared to the 5 over 2 plus 1/3 1 plus x squared to the 3 over 2 plus c. Let's try integrating tangent. So right off the bat, we do not have a very obvious substitution. If we took the derivative of tangent, we would get secant squared, which is not present. So we should rewrite this like we did the previous example into another form where the substitution becomes more obvious. So rewriting tangent as sine over cosine, now we see that there is a function that has a derivative in there. In fact, if I let u equal a cosine, the derivative is minus sine, which is almost the same as that. I just have to put a minus in. Notice you don't want to take the u to be equal this and then get the derivative to be cosine, because if you did that, then you would replace the top, but the derivative wouldn't be present here. You'd have 1 over cosine. So when you're trying to substitute in, you would be trying to substitute in for 1 over the thing that you are, and you would end up failing. So instead we should let u equal cosine x, du equal minus sine x dx, and that way it's in our numerator when we substitute in. And we get that sine x dx, which is what we want to replace, is equal to minus du. So the integral of tangent is the integral of sine over cosine, which is the integral, minus the integral of 1 over u du. But we know that the most general antiderivative of 1 over x is ln x, ln absolute value x. So this is minus ln absolute value of u plus c, which is minus ln absolute value of cosine x when we substitute back in. So at this point, you could just leave it. However, we can make this a little bit nicer by getting rid of our negative. We can do that by using laws of logarithms. We can move the negative 1 outside as an exponent. So we can rewrite this as ln of absolute value of cosine to the minus 1, which is ln of 1 over absolute value of cosine. And then 1 over cosine is secant. So we get ln absolute value of secant plus c. If you have a definite integral, there is still a substitution rule. What you could do is you could either do it like we've been doing, find antiderivatives, write it, and then go back and substitute after you substitute in for u, replace it with x in the end. However, if you want sometimes a much more easy way to do it is to replace the limits at the same time that you replace x with u. Because remember that definite integrals are a lot different than indefinite integrals. Indefinite integrals are functions. So your answer has to be a function of x if you have an indefinite integral. But if you have a definite integral, your answer is just a number. So that means that as long as you replace your limits, you can get the exact same number as you had originally with x instead of u. So you never have to go back and swap back in for x at the end. That last step where we replace the u with what u is equal to will not be necessary if you have a definite integral, as long as you actually go in and replace your limits. So let's do the proof of this really quick. If g prime is continuous on the closed interval, f is continuous on the range of u equals g of x, then we have the substitution rule, but the limit b becomes whatever the function of b was, and the limit a becomes whatever the function of a was. Let capital F be an antiderivative of lowercase f. Then f of g of x is an antiderivative of f of g of x times g prime, so we can apply part 2 of the fundamental theorem of calculus. We get that this is the result of the definite integral, which evaluates as this. So we apply part 2 of the fundamental theorem of calculus again. And then we get that this is equal to the antiderivative evaluated at those limits, which is the exact same thing. So we showed that this side is equal to this. Then we showed that this side is also equal to that. So they're both equal to each other. Let's evaluate the square root of 2x plus 1 dx, the integral from 0 to 4. So let's let u equal 2x plus 1. Right? That seems like the most obvious thing. We would have du equal to 2 dx, and we have dx equal to half du. As we saw before, this is not the only possible substitution, but this will be fine. When x is 0, we have to figure out, for this lower limit, what the new limit for u would be. So u is 2x plus 1. So that's 2 times 0 plus 1. So that's just 1. And then when x equals 4, u is 2 times 4 plus 1, which is 9. So our limits from 0 to 4 become new limits from 1 to 9 when we do our substitution. So this becomes the integral from 1 to 9 of half square root u du, which is half times 2/3 u to the 3 over 2 from 1 to 9. So that's just going to be 1/3 9 to the 3 over 2 minus 1 to the 3 over 2, which is 26 over 3. Notice we did not have to go back in and replace u with what u is equal to, because instead, because we changed the limits, we could just go and straight plug in as if we had a new integral in terms of u. One of the advantages of definite integrals versus indefinite integrals. Remember that this integral is just an abbreviation for 1 over with the dx on the side. We just write this in shorthand. So it looks like we should probably let u equal that thing inside the bottom function. So let's let u equal 3 minus 5x. Then du is equal to minus 5 dx. So dx is equal to minus 1/5 du. Let's change our limits now. When x equals 1, that implies that u would have to be minus 2. And when x equals 2, that implies that u would have to be minus 7. you have to be a little bit careful here. Even though x goes from 1 to 2, where b is bigger than a, 2 is bigger than 1, u goes from -2 to -7, where b is now smaller. That's totally fine. We can integrate, with b being smaller than a, but just have to watch out. Don't try to switch the order. You have to be consistent. So we do our substitution. We get -1/5, the integral from -2 to -7, du over u squared. So that's going to be equal to -1/5 minus 1 over u from -2 to -7, which is 1 over 5u from -2 to -7. So we get 1/5 minus 1/7 plus a half, and that's 1/14. Okay, how about ln x over x from 1 to e? Looks like we should make u equal ln x, then we get 1 over x dx. Perfect. So u equals ln x, du equal, how about dx over x? We could save space. And we get that x equal 1 implies that u is equal to ln 1, which is 0. When x is e, that implies that u is equal to ln of e, which is 1. So we replace our limits and our integral. We get the integral from 1 to e of ln x over x dx is equal to the integral from 0 to 1 of u du. Because the 1 over x gets replaced, 1 over x dx gets replaced with du, ln x gets replaced with du, so that's a super nice integral. We just get u squared over 2 from 0 to 1. So you just have to be careful to replace your limits here. Anyway, this is just a half. Sometimes we have some special functions with symmetry. Suppose f is continuous on the interval from -a to a. Then if f is even, then we get that the integral is just double the integral from 0 to a. So -a to a gets replaced with 0 to a, and we double it. If f is odd, the integral is just 0. So this should sort of make sense. Let's say you've got a nice even function. Say, that was supposed to be y equals x squared, but what are you going to do? Let's say I go from -1 to 1. And I want to integrate. That's this area right over here and this area right over here. It should make sense that if I want that area, I could just look at this part and double it, because it's symmetrical, which is exactly what this says. If I have an odd function, let's see if I can manage to draw x cubed, maybe. Then remember that when the area is underneath the curve, we treat it as negative. So if I want the area from -1 to 1, I have one positive area and one negative area. So they cancel with each other and they give you 0. Let's prove this. Before splitting it into two cases, we're going to split up our integral itself. So we rewrite the integral from -a to a as two integrals. We go from -a to 0 and then from 0 to a. Then we flip one of the integrals. Going from -a to 0 is the same thing as going from 0 to -a as long as you insert a minus sign. Now we do a substitution. Let u equal -x. So then du is minus dx. When u is a, x is a. Or when x is minus a, that means that u is equal to a because we said u is equal to -x. So the integral from 0 to -a, which is this guy over here, now gets replaced. F of x is now f of minus u because x is minus u. Dx is minus du. And a gets taken from minus a, because when x is minus a, u is now a. So that's the exact same thing as taking this minus out, canceling it, and just getting the integral of f of minus u du from 0 to a. So we rewrite our integral. We started with this guy, so we start with it again. It goes now from 0 to a of f of minus u du, plus from 0 to a of f of x dx. If f is an even function, then it doesn't matter what variable we use. It'll always be the same for negative x values as for positive x values when you take the y value. So that means f of minus u will be f of u. So this integral, where we have an f of minus u, we can just replace that with f of u. And then we keep this guy as 0 to a of f of x dx. But if we're going from 0 to a of f of u and 0 to a of f of x dx, this one's in terms of u, this one's in terms of x. Remember, these are definite integrals, so it doesn't matter. You don't have to substitute back. These guys are identical to each other. So it's just 2 times the integral of f of x dx, assuming that f is even. In the other case, where f is odd, now you have f of minus u equal to minus f of u. So when you do your integral, you don't get this thing being replaced by f of u du, you get it replaced by minus the integral of f of u du. Again, these integrals are identical. You've got one positive, one negative, so they cancel and leave you with 0. As an example of this, consider the function x to the 6 plus 1. If you plug in negative x, you absolutely get the same exact y values if you plugged in x. So f is even. So if I look at the integral from minus 2 to 2 of x to the 6 plus 1 dx, that's exactly the same as looking at the integral from 0 to 2, as long as I double it. Okay, so this is fairly easy to integrate. We just get 2 times 1/7 x to the 7th plus x from 0 to 2. So that's just 2 times 128 over 7 plus 2, which is 284 over 7. So the only thing you have to be careful of is you need both an even or odd function, and you need your limits of integration to be a symmetrical interval. So from minus 2 to 2, from minus 10 to 10, etc. How about this integral? Well, it looks like the bottom is an even function, and the top is an odd function. So we would assume our function is odd. You can double check this by plugging in minus x, and you should see that if you plug in minus x, you do get minus f of x. So our function is odd. So if we take the integral of an odd function, by the result that we just proved in the previous page, everything cancels and we just get 0.